let's begin. Welcome to the webinar. We're going to be talking about railroad tracks and how to remediate under them. And the two panelists that you can see here, Ken Cottrell from HGL and Lawrence Seuss from TRS, have been working together for a while, and especially at a really cool site in Brandywine, Maryland, which we'll hear about. There are a few quick details. The webinar is about 30 minutes long, plus 10 to 15 minutes of questions and answers at the end. That's typically the best part, when you guys type in your questions and put them in the Q&A box up on top. Please don't put them in chat. Chat's more for, hey, I can't see the screen or I can't hear anything, technical things. Whereas Q&A is where we pick up the questions you have and we try to read them and answer them at the end. There will also be a new feature at the end. When you are done with the webinar and you sign off, there's going to be just a one-page survey, and we're going to ask you which of 5 topics you like the most for the next webinars. Essentially, we're trying to make it as relevant as possible for everyone. So instead of us coming up with new topics, we have come up with new topics, but we'd love to hear which ones are more interesting to you at the end. So to frame what we're going to be talking about today, we are going to hear about a site where there was TCE and dichlorobenzene in tight soils and in a sand layer, and that were treated under railroad tracks. And you're going to see a site where 1,700 pounds of mass came out. It was heated to 106 degrees Celsius on average, so boiling, steaming conditions. And you're going to wonder, can you do that safely without subsidence, without movement of tracks? So just to set the stage real quick, from a technical standpoint, what can happen, the two main things that you're nervous about when you're doing thermal treatment and you don't want any movement. One is oxidation of organic materials. It could be a peat layer, for instance, that get exposed to oxygen and vacuum and high temperature. You can see shrinkage of peat layers. You can also see some loss of organic mass that's coating quartz grain, for instance. So that could be an issue. The other thing is clays. There are swelling type clays like smectite, montmorillonite. If you change the water content, they may actually change their volume. So those two things basically are the things we worry about, that could lead to some change in volume down below the ground. But let's get into the site in question. I'm going to ask you, Ken, to talk about the overall Brandywine site. I know it was a combined remedy, and you had a lot of years managing this site, and would love to hear from you overall how the site was attacked, please.
All right, thanks Gorm. Good afternoon, everyone. Yeah, the site had coupled remedies before. Coupled remedies, I think, was even a thing. I know it is a thing now. So just a little bit about the site. It's a former storage area for excess property from DoD facilities in the DC area. So throughout its history, spills, leaks, etc., basically yielded a TCE plume to the tune of 21 acres that extended from a corner of the site under railroad tracks, under a public road, into a residential area. There was also a smaller co-located 1,4-dichlorobenzene plume, as Gorm mentioned. So anyway, HGL, yeah, it was a lot of years. We were awarded the contract in 2006 from the Corps of Engineers Omaha District to implement the interim remedy that was in the interim rod in 2006. So again, coupling of remedies had two elements. One was a pump and treat system to hydraulically control the more concentrated, more contaminated part of the plume. And just the photos there, we dug a 225-foot long recovery trench, keyed into the aquitard about 30 feet down. That's the pump and treat building. So that was one element of the remedy, hydraulic control of the source area. The other element was injections to do bioremediation. We also had to inoculate with bugs because there were no DHC there to munch on the TCE. Injections of lactate, ABC, EHC with zero valent iron to basically break down the TCE all the way down to ethene. So I think we can go to the next slide. So that's what the plume looked like in January 2007 when we inherited the site. You know, like I said, it's 21 acres, 21 acre TCE plume. That dark area in the middle, upwards of 50,000 parts per billion of TCE. So pretty high concentrations there.
It may be difficult to see, but this bar down here is 360 feet, right? This is like
right.
110 meters. So that's the length of a soccer field, just in comparison. You had a pretty decent sized plume.
Yeah, and you can also see, I guess I'll point out too, that the railroad tracks, you can see the railroad tracks, might be able to see them a little better later, and the road, but everything emanating from that back corner of the site.
Yeah.
So I think we can go to the next slide. So operated the pump and treat system for 5 years. We got 12.5 million gallons of groundwater out of the ground and 90 pounds of VOCs. Remember that number when we talk about the mass removal from thermal? Gorm already said it in his intro, but if you missed it, we'll say it again later. So 90 pounds of VOCs, not a whole heck of a lot. That's about a bucket full of TCE. Injections, over 2,000 points we injected. Like I said, it was lactate and sugar water and oil, and then more oil than lactate, and basically cleaned up the whole plume. We took a 21 acre TCE plume and got it down to less than 3 acres. So we achieved MCLs throughout the entire area that the pump and treat system didn't have hydraulic control over, including all of the residential area. So that was a huge success. And maybe go to the next slide, Gorm.
And real quick, so the pump and treat only took out 90 pounds. Do you have any idea how much was degraded, or is that just unknown?
Most of it was TCE.
Yeah.
So most of it was TCE. We had a lot of cis. We didn't have a lot of vinyl chloride generated at this site. And I think in part because we had residual DNAPL in the clay that was pretty much 100% TCE. So we didn't have a lot of breakdown. And there had been an absence of DHC bacteria to break it down anyway. We had to add that.
All right.
So yeah, tremendous success. So by 2015, like I said, we reduced the plume down to less than 3 acres, MCLs throughout the entire residential area. We had the source area under hydraulic control. But of course, what we're noticing is now with the pump and treat system, we're pretty asymptotic, really diminishing returns in what we're getting there. And someone really smart at EPA once said to me, remedy implementation is the final stage of site characterization. And what does that mean? Sources really reveal themselves as your remedy progresses. So what we saw here at Brandywine was when we would have the pump and treat system down for a month for maintenance, we'd start observing rebound in a lot of wells. And that gave us a clue on what was going on, that we had a potential back diffusion problem here. So we use some really cool tools that most folks are familiar with. We use Mip, we use passive flux meters, and we basically gridded the site to define the source area. So maybe go to the next slide. So these are the Mip results, and I love the graphic on the right. That red area is the source area. So using Mip, we were able to draw a box around the source area, and that's the source that's in the Calvert Formation, in the clay. What's interesting is you'll see sort of a break, and then you'll see on the left-hand side some red. That's contaminated groundwater. That break is where the recovery trench is for the pump and treat system. So what this really illustrates is that you've got the stuff back diffusing off the clay, and it's in the groundwater further down gradient. So what's bad about this is if you let this keep going, what's in the groundwater further down gradient, that mass can actually load back into the clay down gradient and exacerbate your problem. We use passive flux meters, and what they do, without getting lost in that, you can calculate the rate of diffusive flux of your source into groundwater. The MIP allowed us, with some real soil samples, real analysis, to do a rudimentary mass estimate. And when you couple that with the rate of diffusive flux, we arrived at it's going to take over 100 years if it's linear to deplete the source, and we know it's not linear. So that over 100 years basically tells you need to get an aggressive source area remediation technology in there to take care of it. So that was quick. That was a mouthful.
That's awesome. Lauren, I know you were the project manager at the time for TRS, right? Can you tell us a little bit about the ERA implementation and the challenging conditions you were facing?
Yeah, definitely. So Ken was key in identifying the target treatment area for us and that depth. Without that information, we really couldn't get started. So the outcome of that that high resolution site characterization was really used by TRS to target an area that ended up being about a little bit less than an acre. And all that work was done, with support from the Air Force and contracting ultimately under a performance-based remediation contract with the Corps.
Yeah, shout out to the Omaha District Corps and the Air Force for their steadfast support and confidence, in this project from day one. So
yeah. So this is what that target treatment area looked like. This is what was represented of the source. So the trichloroethane and 1,4-dichlorobenzene that we had mentioned previously. Now we've got an outline. What you can see from the aerial photograph are really two, I think, prominent site features that jump out to me. It's the CSX railroad tracks right there in the middle, and then the county roadway a little bit left of the tracks. So those were really key features that definitely added to the complexity that we needed to design around. But what that heating system looked like conceptually, if you could skip over to the next slide, Ken had us targeting residual DNAPL in that calvert formation, that deep clay that's shown here in the conceptual site model. So we were targeting, we needed to ensure heating of that target clay, but also throughout the water column underneath those railroad tracks. To ensure that we could collect steam from what very little vadozone existed at the site. We ended up using 2 different electrodes that were deployed as part of our heating system. And so those electrodes, that heating system was designed around a lot of site features, which again, just added to the complexity. If you could skip to the next slide. Thanks, Gorm. So here you can see the layout of the site. Again, this is final stages of construction. We're getting ready to flip the switch and turn on the system. But you could see how things were divided by the tracks in the middle. We were working, both within the CSX right-of-way, but also the county right-of-way. It literally split the site in 2. So, Ken and I had to work within 2 different equipment compounds. That meant tools on either side of the tracks, heavy equipment on both sides of the tracks. From a construction point of view, it definitely required a lot of pre-planning. But also, utility power and making sure that we had access to the grid on both sides of the tracks was also something that we needed to design around. There were restrictions with regards to overhead lines that were present at the site. What's pretty common alongside these railroad tracks is high voltage utility lines. So we were working within, those conditions as well. Lots of site work and planning went into the flooding conditions that existed at the site, although not designated as a a wetland, we really had to think about where we place the equipment, especially between the railroad tracks, which was, again, very prone to flooding, literally water flowing over railroad tracks at time during construction. So lots of different features to design around.
What are these little gray boxes around the well field?
Yeah, so those are field transformers. So we get our power from the utility, and it's coming from our power control units. Those are the very large gray boxes in the equipment compound. And then we're able to step down voltage or boost voltage using a variety of different field transformers. What you're seeing in the field here at Brandywine are actually step down transformers.
Awesome. You mentioned two different types of electrodes. I'd love to hear more about those and why two different types.
Yeah. In fact, I've got a site plan. There you go. So two different electrodes, right? We've got two different blue shapes that are represented in this site plan. Again, that orange yellow line around, that's the line that Ken drew for me and my team. And what we needed to do was design infrastructure, heating infrastructure to ensure heating of that entire volume within that line. So we love sheet pile electrodes. We actually rate our ERH sites on sheet pile goodness as part of our early modeling that we do. Those sheet pile electrodes are actually represented as the blue rectangles in this site plan. And really why we needed to use two different kinds was because of the overhead restrictions. It prevented us from using sheet pile electrodes across the whole site. So when we were working under and around the high voltage power lines, we were doing a more typical board electrode. So with regards to power delivery and comparing the two, we can deliver twice as much power to the subsurface using sheet pile electrodes in comparison to a traditional board electrode. So what you see there in the site plan is we've got two board electrodes that are actually spaced really close together anytime we weren't able to use a sheet pile electrode. So those two board electrodes were actually on the same phase. They were working together to try to deliver as much power as a nearby sheet pile electrode. The next slide, you can actually see that infrastructure, the heating infrastructure going into the subsurface. So on the left-hand side, you see a sheet pile electrode that's literally propped up right now, resting against the ground surface, getting ready to be driven into the county roadway. And it's being done so using a pile driver, but that sheet pile is 35 feet long. You could see a 50-foot tree in the background just for a quick point of reference. So, with regards to overhead clearance, you could see why that becomes an issue when working around the high voltage lines. Over on the right-hand side, you're looking at just a sonic drill rig compact crawler. It has a much lower mast in comparison and is easily used underneath power lines. But also, one thing to point out about that drill rig is it's relatively easy to move in and out of the right-of-way during train passings, which unfortunately happened to us quite a few times during construction. So
almost daily.
Yeah. we got to see lots of trains out there.
I'm gonna cheat and take a question already because Matt Ingram has sent a really good one. He says, "What kind of access requirements were you guys facing doing this? This looks like you're getting really close to the tracks." And Ken, maybe the best one for answering that one.
Yeah, I can tackle that one. At the risk of sounding cliche, it's communication first and foremost. There's a lot of early engagement with CSX, with the railroad. We brought them in at the feasibility study stage and basically, kind of sat around a table and said, all right, what's going to work for you guys? What's not going to work for you guys? You also have to understand when working with the railroad, you have to work with multiple entities, and it sort of starts with real estate, and then you're working with environmental, And then you're also working with engineering from an operational standpoint. So really understanding that there's multiple entities you need to interact with. But kind of at the end of the day, what's common in railroad corridors, utility corridors, right? So CSX has all kinds of, as do other railroads, they have all kinds of plans and specifications for pipeline installation, for sheet pile installation. They're right on the website, and what we're doing here is not much different than those things, right? It's a construction project at the end of the day. So I don't know, Lauren, I think there's a slide that shows like some of the jack and bore stuff we had to do per their specs on the next slide.
Yeah, as Ken mentioned, these are specifications that are readily available, right? We knew that we couldn't just lay our infrastructure over the tracks, and nor could we put it over in some kind of clearance or crossing. So if you can't go over, you've got to go under, essentially, and that's what we did here. On the left-hand side, what you're looking at is a very large trench. This is where we installed conduits, literally underneath the railroad tracks. 4 different conduits in the end. You could see them daylighting on the right-hand side, but one stretched all the way from one side of the tracks to the other, and that gave us power on the other side of the tracks. And then we had 3 going from the center to one side, and that was really to help with the operating electrodes and the equipment vapor recovery efforts that were happening in between the tracks. So when you can't go over, you got to go under. But don't you think, Ken, a big key aspect for CSX was monitoring in the end?
Yeah, monitoring in the end. I just before we get to monitoring, yeah, that is key, and I think that's where we get sort of into the meat of this. The other thing, just to circle back, a lot of safety requirements and training needed. You need roadway worker training that's mandatory for working within the railroad. I think the other thing I wanted to add is that the railroad was actually pretty excited about this project. We've been going on site for years. We've been doing MIP. We've been putting in wells. We've been sampling, and thermal to them represented the end of those incursions, because I think the railroad understood the finality of thermal versus, let's say, ISCO, which was contemplated, which again would have been several years of injections, re-injections. They were pretty excited about the ERH remedy.
Very good. Well, let's get to the track monitoring. Essentially, I'm very curious to know whether you derailed any trains, for instance, because
no, that didn't happen.
Cooking.
You make us giggle, but that's like literally what nightmares were at the time. Yeah. I've got a picture of the track monitoring system once it was deployed. So obviously, to address any type of subsidence concerns, there's the design, there's communication that's happening, but at the end of the day, we needed to have the data to back it up, right? We deployed an automated motorized total station is what it's called. It has survey prisms all over the site, all over the railroad tracks. They're located about 10 feet on each rail. So there's 4 different rails at this site. And there was this station, this device that was actually mounted onto the signal you're seeing in the photograph on the bottom right-hand side. And that scanning station scans the horizon every few hours and collected elevation changes at each and every one of those survey prisms that was mounted onto the rails. So data was collected, sent to a cloud, real-time access was given to project team members, and alerts, were also sent in order for us to ensure that we were staying well below the thresholds. So the next slide, there's, just Ken mentioned that CSX has rules and specifications. I'm sure it comes as no surprise that they also have threshold limits. They know that their tracks can take a certain amount of movement, and we need to ensure that we're staying under the allowable movement, right? So this is just a snippet of one of the thresholds we needed to stay below. Basically for this one scenario, their limit's 3 inches. And, my goal, Ken's goal, was to monitor and ensure we didn't even get close to their limits. So we set up various different notification levels and actions that had to occur, which included, physical inspection of the site if needed. One thing I want to note is, data transparency was really key during this phase of the project, especially operations. So setting up alerts, monitoring alerts that included CSX receiving notifications if we got to any of these action levels. That was so key at the time. But what this meant in the end is like so much data was collected, overwhelming amounts of data was collected. I have a very small snapshot of data that was collected over a 1-week period at a single monitoring location, during a busy time in the project. So bear with me. Again, it's just a teeny tiny snapshot, but the blue line that you're seeing there in the middle of this graph, that represents the movement of the track at that one location, measured right in between the 2 different rails. What you can see is, the deflection, the cycle that the movement has up and down over a 24-hour period. The yellow and blue lines at the top and bottom represent the maximum and minimum deflection measured at the control points, which are outside of the treatment area. But when looking at the orange line, it may look like there's 2 different exceedances that occur outside of that min and max, but really what the orange line is representing is simply the change in ambient temperatures. So you can really see the correlation, right, Gorm? I mean, as the temperature is going up, you see there is some flex, there's some movement of those rail lines. So ultimately, in the end, massive amounts of data collected, both during construction and operations. We did see movement that was very reflective of this kind of daily cycle. It all ended up being associated with ambient temperature changes, well below the threshold limit that CSX had for us, and even below the notification levels that we set for ourselves.
So that movement from top to bottom or peak to valley, that's like 2.5 millimeters.
Yeah, exactly. Yeah, less than a quarter of an inch. Yeah.
Okay, good. So no derailment of trains.
Stop saying that, please.
No, and we after a while we slept better at night.
Yeah. Absolutely.
All right. Ken, real quick, can you repeat to us what the remediation goals were and what a successful outcome of the remedy would look like?
Right. So the final rod, this was the final rod, was basically, we didn't have a number in there, but it was reduce the mass of TCE and dichlorobenzene such that it would not continue to back diffuse and impact groundwater. Right. So that's the plain and simple RAO. And of course, part and parcel to that is do no harm, right? Do no harm to the tracks, do no harm to the road, et cetera. But we deal in a real world of contracts. So contracts likes to put numbers to things, right? So the number was actually MCLs in groundwater for TCE and 1,4-dichlorobenzene. So, in hindsight, that seems almost insane to take a site with residual TCE DNAPL to MCLs. But okay, so yeah, we can do that, fingers crossed behind our back. We will, certainly. So, and it's a performance-based contract. So you're getting paid for that performance. So we got there and we boiled the heck out of the site, right? And slowly but surely MCLs there, MCLs there, MCLs there, until we had no more groundwater. because we had boiled the site for so long and depressed the water table, consequently, all we had in our wells was steam. So this is a problem, as you might imagine. So what we had to do was really go to other, I'll say, more traditional ways or typical ways of defining success, with a thermal treatment remedy. And Lauren, maybe you can go through some of those, the multiple lines of evidence that we used.
Yeah. Yeah, so, in some of those trickier areas, as Ken described, where we weren't able to collect the representative groundwater samples that we had originally set out to collect, we ended up relying on various different lines of evidence. The first metrics was temperature. So the yellow line, plotted there against the secondary axis told us that we had been boiling at this site for over 4 months. That's a data point that became really important as we were trying to figure out had we reached conditions with TCE and 1,4-dichlorobenzene that we could expect if we had access to representative groundwater samples that we were at or near the MCL. So we relied on temperature data. We also evaluated the NAS removal rates and overall cumulative NAS removed. At this site, the gray line represents the cumulative NAS removed, about 1,700 pounds in the end. It certainly showed that we had gone past our peak extraction time, which was really during the initial heat up. So we had already passed that. We were really approaching asymptomatic conditions at that time. Despite the long stretch of boiling conditions, we were no longer removing significant mass. We had boiled relatively all the VOC mass out, and we knew we were boiling relatively clean groundwater that was moving into the treatment volume. So, Ken, I know you did a lot of work with stakeholders at this time, but ultimately we all concluded that we were going to shut the system down, despite not having some of that hard data that we originally intended to collect that showed the groundwater had achieved MCLs. So it allowed us, some time for the water to recharge. We made that decision to shut the system down. Water started recharging, ambient groundwater flow conditions started to return, and we ended up being able to collect some confirmatory groundwater samples, which did in fact show that we were able to confirm MCLs were achieved. So this is a plot just showing before and after TCE concentrations in groundwater at the site. Overall, we were able to achieve 99.9% reduction of TCE. And of course, the fun one, 1,4-dichlorobenzene, some before and after data from that particular contaminant shows, in addition, we achieved MCLs for 1,4-dichlorobenzene. So
right,
all this.
That's the fun one, because the boiling point's higher, right, than
Yeah.
TCE.
Yeah.
So that's what makes 1,4-dichlorobenzene a little more challenging, for sure.
Yeah, absolutely. So we did it without the derailments that Gorm keeps on talking about. That's another exciting, data point too, I think, is we were not damaging to the railroad tracks during remedy implementation, despite all the boiling off of groundwater that we saw at the site.
Yep.
Yeah. To get this type of reduction for 1,4-dichlorobenzene, you have to boil a large fraction of the pore volume, right? At least according to laboratory studies and things I've been involved in, something like 30-40% of the pore volume you need to turn into steam that then migrates out in order to reduce 1,4 DCB this much. So, and the fact that there wasn't water in the monitoring wells to sample in some of them, it does show that we somewhat desaturated a lot of the site. And it's nice to see then that there wasn't any subsidence caused by that, because we heated it to boiling and we pulled vacuum and pulled in oxygen via atmospheric air, right? So we created conditions that if there had been a lot of organic matter, there could probably have been some oxidation, but that wasn't the case here. That was good.
Yeah.
Yeah. Ken and I were sleeping better at night.
Yes, for sure. So it was a very, very phenomenal outcome.
Yeah. And now it's time to move into the Q&A, and there isn't that many questions in there. So if you're listening and you have more questions, please start putting them into the Q&A tab there. I'll read a few. What was the duration of the cool down and groundwater recharge? Essentially, how long did it take before we could get reliable groundwater data? I would think is the question.
Yeah, so we were able to collect groundwater samples after about a month of a shutdown period. So it took a little while for us to have measurable groundwater at select wells. Obviously, it doesn't all recharge at the same rates at the site, right? So some areas never dried out, other areas were a lot more difficult. So I'm referring to the more difficult areas when I say about a month.
And then the other thing we did, we did quarterly monitoring per the record of decision after shutdown. And a year after shutdown, groundwater temperatures were still around 50 degrees C, which was pretty amazing, really, that it retained that much heat. I think the site heated up, Lauren, one or 2 degrees C a day, maybe more to
a
2.
day. Yeah, 2 degrees a day until we got to about boiling, and then we held that temperature obviously for extended duration.
Yep.
Tommy Jordan asked the question that we often get: how much did all this cost? And I'll remind everyone that the treatment volume for the thermal was somewhere around 50,000 cubic yards of subsurface material, right? Lauren, do you remember roughly? You managed the project.
Yeah.
What was the sum of the thermal?
Yeah, so for our costs, right, and that's not inclusive of the whole project, but our costs were about $200 per cubic yard. That's how much it costs for TRS to design, construct, operate, and demobilize a system like this at this site.
And I think I did an estimate that came out to something like maybe $160 per ton. I can't remember exactly, but it was somewhere in that neighborhood. So it's definitely a competitive number in terms of, if you had to dig and haul all of this stuff. The other big consideration. Yeah, it was hardly an option, because what works and what doesn't work with CSX, closing down their tracks to do dig and haul, that didn't work for them. So not an option.
Mm-hmm. Yeah. Mike Palmer asked if there's an estimate of total mass removed from all technologies. I think we've somewhat covered it, right? 1,700 pounds thermal, 90 pounds with pump and treat, and then we don't know how much degraded with all the injections and all the bio, right?
Right. Yeah, that number is pretty hard to arrive at, but yeah, that the big disparity is 1,700 pounds thermal, 90 pounds pump and treat. Folks can make their own conclusions about that. So.
Yeah. Were concentrations, was soil sampling done before and after is another question. That's a good question.
We did soil sampling before, and that was really to arrive at our mass estimate. We did not do soil sampling after, because the groundwater really tells the tale, and some of those lines of evidence that Lauren went over really tell the tale in terms of, hey, is there any mass left down there? And you can see the answer was no, there was no significant mass. Therefore, EPA didn't feel compelled to make us do any soil sampling.
Okay, that's good. Yeah, I would say if the groundwater concentrations were higher, then you would be more compelled to go look and see where that continuous source was, right? And you could do that with drilling. It would probably have been back diffusion from the clay layer if the clay layer at the bottom had not been properly treated. then that would be a source, basically, of recontamination. Yeah.
That's why the MIP was so important, making sure during that phase of site characterization that you go deep enough and make sure you hit clean so that you don't have that uncertainty on the back end.
Yeah. There's a question about piping infrastructure for vapor recovery and recharge of water. How did you install basically the vapor extraction screens and pipes? Was it done with horizontal drilling or what? Lauren, maybe that's one you can explain.
Yeah, so at this site, there was a relatively high groundwater table. And so although we were targeting deeper clay, we heated the entire groundwater column and then collected vapors in the relatively shallow vadose zone. But we also built at the site artificial vadose zone, or a vapor recovery plenum. So we brought in gravel, used a liner to cover that up, and put inside of the imported gravel vapor recovery screens throughout the treatment area. And a vacuum was applied to those vapor recovery screens. They're horizontal screens that were installed in that plenum layer at the surface of the site. We also used some vapor recovery chimneys throughout the site too, to collect vapors at other areas. But that's the approach with vapor recovery that was used at this site. I think there's another follow-up question about vapor recovery and how we were able to collect vapors in between the tracks. And that was actually through those jack and bore conduits. We were talking about CSX's procedures with drilling underneath the railroad tracks. So we collected vapors using a conduit that was put in place using jack and boring, and jack and a bore type of conduit installation is slightly different than directional drilling. But CSX has very detailed specifications on how one might put a conduit via jack and bore in place underneath their track. So that's what we ended up using at the site.
Wow. I have a question from John Haas. Hi, John. I may just a little bit, but he's basically saying, tell us about the performance guarantee and contract terms. Maybe rephrasing it a little bit, Ken. You've been out there. Rod was from 2006, and you basically gambled on this ERH remedy working in less than 1 year, so that source material would be gone and the remedy could be shortened. So in other words, how could you be so confident that it would work, and how did you transfer that responsibility to the thermal contractor?
Yeah, so HGL, we were a glutton for punishment because this was actually, two different performance-based contracts. One awarded in 2006 for the interim remedy, and then this one in 2012 for the final remedy. So, the number was MCLs, and we knocked on a lot of wood and crossed a lot of fingers. But honestly, thermal, TRS and HGL really worked together a lot during the proposal stage to make sure this was achievable. And we had the confidence because of the source area characterization, because of our mass estimate, because of the data we had on the front end, we were pretty confident that okay, we will achieve these MCLs, and that was a condition of payment. So nobody got paid if we didn't hit MCLs. And I don't want to give folks any ideas out there, but would I do it again? Well, I know it was successful, but yeah, there were a few tricky sleepless nights over that, especially when we ran out of groundwater. So
yeah, that was definitely a stressful time. But yeah, as Ken mentioned, it was built into payment milestones, right? TRS
right.
and HGL had real skin in the game to make sure that we got to those levels eventually.
Yep. I see one more question, and probably the last one we'll take because we're out of time now. Terry is asking if we analyze for daughter compounds and whether you continue to sample to look for rebound in the future.
Yeah, so we did analyze for daughter compounds because they were COCs in the rod. So we had to demonstrate that MCLs for those were achieved, and we never found any daughter compounds. They weren't there to begin with, and they weren't there after thermal treatment. So yeah, no daughter compound generation.
Yeah.
Monitoring for rebound. So, you know, if you've removed all the mass from the clay, you don't really see rebound, and that's what happened. What you will see though is areas outside of the thermal treatment area and the area between the tracks, which just by virtue of engineering was not I'll say was not treated as much as some of the other areas. We did see a little bit of what I'll call recontamination, where TCE levels did go up a little bit, and I'm talking, you know, tens of parts per billion, not hundreds or thousands, which would, you know, indicate there was source material left. So we did see a little recontamination as TCE and groundwater from other areas entered the thermal treatment footprint, but nothing that was alarming to anyone.
Fantastic. Thank you, both of you, for this very informative stuff. Just a reminder for everyone, when you try to sign out, there will be a survey, and we'll ask you, and these are actually the 5 potential topics of future webinars. We'd love to hear from you guys which ones are more interesting to you, and so we can use those, pick those for the future. Thank you so much, and have a wonderful day.
Thank you.
Thanks, Gorm. Thanks, everyone.